Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 3.7 titled Partitions. So this section is really about breaking a setup into non-overlapping pieces. That's what a partition is, alright, and we'll see that here. So partitions, alright, so two sets A, so before we get to the definition of partition, we need to learn a couple other definitions. So two sets, A and B, are said to be disjoint or mutually exclusive. You might see those words in some other texts. So two sets, A and B, are said to be disjoint or mutually exclusive if their intersection is empty. Right, so they have nothing in common, no common elements. A sequence of sets, say A1, A2, A3, up to AN, is called pairwise disjoint if every pair of distinct sets, so every pair of different sets in the sequence is disjoint. So in other words, AI intersect with AJ is empty for any I and j in the range from 1 through n where I and j aren't the same. All right, because obviously if you did AI with AI, that wouldn't be empty. All right, any set intersected with itself is non-empty except the empty set. Yeah, so a sequence of sets, a collection of sets, is pairwise disjoint if you took any pair of them and that each pair has nothing in common. So basically there's no overlap between any of the sets. Okay. So now a partition of a non-empty set A is a collection of non-empty subsets of A such that each element of A is in exactly one of the subsets. A1 through AN is a partition for a non-empty subset of A if the following conditions hold. So for each set, for each I, AI is a subset of A. For each I, AI is not empty, right? Not equal to the empty set. And A1 through AN, all the sets form a sequence of sets that are pairwise disjoint, right? Meaning if you take any pair of them, their intersection will be empty. And finally, the set A is the union of all those sets. Right? So like I said, putting all these together, a partition of a set is just breaking a set up into non-empty pieces that don't overlap, right? That don't have any common elements. It's more simply put. So they give you a little animation down here. See, set A is the collection 1, 2, 3, 4, 5, 6. Just break this up into some non-empty pieces with no overlap. 1, 4, 5 for A1, 2 and 3 in set A2, and 6 in set A3. See how these are pairwise disjoint? If you take A1 and A2, they don't have anything in common. Take A1 and A3, they don't have anything in common. Take A2 and A3, and they don't have anything in common, right? So these three sets are pairwise disjoint, and the union of all three of these sets is the set 1, 2, 3, 4, 5, 6. So they would say A1, A2, and A3 here form a partition of set A. And I'll play the animation. And they say break it into non-overlapping pieces. Right? Simple as that. And then they have another example with like a number line. And here's the real number line. And if you break up the real numbers into all the values less than 1 for B1, the values from 1 to 3, including 1 and 3 for B2, and all the values greater than 3 for B3, these sets here, B1, B2, and B3, they're said to form a partition of the real numbers, a partition of R. Because again, these are pairwise. They're all not empty, right? They all have some numbers in them. They're pairwise disjoint, right? If you take B1 and B2, no overlap, right? They don't share any numbers. B2 and B3 don't overlap. They don't share any numbers. And B1 and B3 don't overlap. They don't share any numbers. So they're pairwise disjoint. And their union, if you took the union of all three of these sets, you'd get the whole real number line. You'd get the set of real numbers. Right? So these are, they form a partition of the real numbers. They're the real numbers broken up into, non-empty subsets that don't overlap, that are pairwise disjoint. Okay. All right, so we're asked in the participation activity, and I'll draw some pictures. All right. For each question, indicate whether the sets form a partition of the universal set. So number one, the universal set is the real numbers. So I'll draw a number line. And here are our three sets. So I'm going to go to some paper here and get this drawn for you. Okay, so here's the sets that were mentioned in this activity. The universal set U is all real numbers, so I've represented that here with a number line, all real numbers. We have these three sets, and I'm going to represent them with some graphs. So set A1 is all the real numbers that are less than or equal to -4. Right, so let's say -4 is here on the number line, and I'll draw that here. Now equal to -4, meaning -4 is included. And then, -4.5, -5, negative whatever, all those numbers. There's a representation of set A1, this graph I just made. A2 I'll do in like a blue color. A2 is the set of all the reals that are between -4 and +4. So there's -4, let's say +4 would be over here. Now just between them, not equal to them. So I'll put that above. Right, so again, an open circle telling me that -4 is not included. Same thing with +4, an open circle to let me know that 4 is not included in this set. And then all the numbers in between are included, right? So here's A2. And then this pink color I'll represent A3. I have this set A3. That's all the real numbers that are greater than or equal to 4. So 4 is included. All right, so a little solid dot there above 4. And all numbers greater than 4, 4.5, 5, 6, 7, and so on. That's all these numbers here. Here's A3 represented by that graph. Now the question is, do these three sets form a partition of the real numbers? All right, well, first off, they're not empty, right? A1 is not the empty set. A2 is not the empty set. And A3 is not the empty set, right? They all have something in it. They all have some numbers in them. So they're non-empty, right? That was one criterion. They're non-empty. The second criterion was that they are pairwise disjoint. All right, so let's check that. Are they pairwise disjoint? Meaning if I take any pair of different sets, so look at A1 and do the intersection with say A2. Do they have any overlap? Well, A1 intersect A2, you can see up here, A1 intersect A2, there's no overlap, and that's an open point, that's a closed point. This has -4, this does not. So this is empty, but you can't just do one pair, right? For a bunch of sets to be pairwise disjoint, you're going to have to take a look at all pairs of different sets. So A1 and A2, how about A1 and A3? What's A1 intersected with A3? Well, A1 with A3, clearly these don't overlap. They don't share any numbers. So this is also empty. They're disjoint. And finally, the only other pair I haven't touched on are A2 and A3. Look at A2 and A3. So A2 is this set, A3 is that. They don't overlap. Again, 4 is an A3, but not an A2. There's no overlap. There's nothing in common. They are disjoint. And those are the only, there's three sets, so there's three different pairs, and I checked all three pairs. So the second condition is satisfied. They are pairwise disjoint. Oops, can't spell. Pairwise disjoint. All right, so I got check on non-empty. All three are non-empty. Check on the three sets are pairwise disjoint. Then the only other condition to be our partition of the real numbers is, are the real numbers equal to the union of these three sets? Well, let's take a look. So look at the union, A1 union A2 union A3. If you put all three of these sets together, this does make up the entire real number line, right? Because here's A1, right? And then I put A2 on it, and then I put A3 on it, which will give me the 4, and there's A1 with A2 with A3. That does make up the entire real number line. This is equal to the reals. So the union of all these sets makes the universal set. All three of these sets are pairwise disjoint, and they're non-empty. All three of these conditions hold. So A1, the set A1, A2, and A3 do form a partition. A partition of the real numbers. Okay. Right, so back here, yes, they do. All right. Again, they're mutually disjoint or pairwise disjoint, and cover the set of all real. Their union makes the set of real numbers, and they're non-empty. Right? That was another condition. Remember up here, they have to be non-empty as well. And all be subsets of the universal set. I didn't state that, I guess, right? Because that was the case. All right, this one. Now this one I'm just going to kind of say out loud. Here the universal set is remember Z plus means the positive integers. So that's 1, 2, 3, 4, 5, 6, and so on. But starting at 1. Alright, so here are the 4 sets in question. And they're asking, do these 4 sets form a partition of the positive integers? Alright, so A1 is all the positive integers that are prime. Right, you know what, maybe I should write this one out. So I'll be back on some paper in a second. Okay, so here are the sets that were given in that part of the activity. So the universal set is a set of positive integers, and that's 1, 2, 3, 4, 5, and so on. A1 was a set of positive integers, so it's it's a subset of this universal set, such that they're prime. Right, so I'll start listing those off. Remember, primes are bigger than 1. Right, so 1 is not prime, and the numbers that their only divisors are 1 in itself. So 2 is prime, 3, 5, 7, 9 is not, right? 11, and so on. Okay. A2 is made up of positive integers, so another subset of this, that are odd and composite. Right? Composite means it has a divisor between 1 and itself. So this would be like, again, the odd and composite. So remember, 1 is neither prime nor composite, so 1 is not in here. 3 is in the prime 1, 5, 7, 9. Right? 9 is composite and odd. 11, 13 is prime. 15 is odd and composite. 17 is prime. 19 is prime. 21 would be in here, and so on. Right? Okay. A3 is all the integers that are even. All the positive integers, right? So positive integers only. So let's start with 2. 2 is even, and 4, and 6, and 8, and so on. And the last set, A4 here, is just the set with the number 1 in it. Okay, so these are all subsets of the universal set. Right? That was one condition. They're all non-empty. Right? A1, A2, A3, and A4 are all not the empty set. Right? They all have at least one number in it. So that was another condition, right? They're all non-empty. Check. Are they pairwise disjoint? Are they pairwise disjoint? So I'll start checking different pairs and look at their intersections, seeing if they're disjoint. How about A1 intersect A2? So A1 and A2. Now these are primes and these are odd composites, so they'll have nothing in common. This is empty. But that's not enough, right? Just showing that one pair of the sets is empty, is disjoint, that's not enough to show that all four are pairwise disjoint. You have to look at all possible pairs. And if they're all empty, if all possible pairs are disjoint, then the collection of sets is pairwise disjoint. So how about A1 with A3? Let's see, A1 is these primes, 2, 3, 5, 7, 11. A3 is the evens, 2. Oh, look. They do share something. And that would be the only number they share, right? The only even number that is also prime is the number 2. This is not empty. So I can stop now. Right? These sets are not pairwise disjoint. A1, A2, A3, and A4 are not pairwise disjoint or mutually disjoint. And since that's the case, since they actually have some overlap, right, then they can't possibly form a partition of the positive integers. Now their union is the positive integers. Right? If I take the union of all these sets, I'll have every positive integer. It's just that some of these sets have some overlap. Right? So you're not breaking the positive integers up into non-overlapping pieces. That's what a partition is. You break up a set into non-overlapping pieces, but there is overlap here. So, noting all this, A1, A2, A3, these sets that I have here, and A4, do not form a partition of the positive integers. Form a partition of Z plus. Okay. Because they weren't pairwise disjoint. So they're not mutually disjoint. And I'll let you figure out the third one. Alright, so again, pretty easy, I feel. To set a bunch of subsets of a larger set, form a partition of that larger set if their union makes the larger set and they're pairwise disjoint, right? They're not overlapping, none of them are overlapping. Breaking a larger set up into non-overlapping pieces, non-overlapping subsets, that's a partition. Okay. And then you have your additional exercises. Right? Some of these are on assignment 4, some are not. Again, I would recommend that you do all the problems anyway, just for extra practice, extra exposure to the material. Get better at it. And yeah, if you have any questions, let me know on any of the problems. You can always also check the solutions to see how you're doing, see how you're grasping the material. Please try to do the problems, work on them, try to finish them, do them the best you can before you look at the solutions. Because if you just look at solutions and just copy down the solutions without trying to work on anything, you're not going to learn anything. You're not going to get better. And it'll make exams that much tougher. Alright, so that's all I got for section 3.7 on partitions. And I believe, yes, that is the last section of chapter 3 on sets. Right, now, that doesn't mean sets are going to go away. But these are just this is just the last section of the chapter on, specifically set focused. Sets will still be involved in the course. So that's it for chapter 3, section 3.7 here. Let me know if you have any questions, of course, and thank you very much for watching.